All right, so next up is 5 things. So we're thinking about a central atom and then 5 attached things. So if they're all atoms, an example of this would be PCl5, no lone pairs or anything. And so if you think about the way this would look, here it is. You have one going above, one below, one to the left, and then one going behind the board, and then one coming out of the board. And so if you're thinking about this bond angles here, between these 3 kind of center ones and the bottom ones, it's going to be 90 degrees. And then in between all these center ones, it's going to be 120 degrees. And so you can see we kind of have this triangle here, and then we kind of have 2 pyramids, one going above, one going below. And so triangle, two pyramids, this is called trigonal bipyramidal, right? So it makes sense. Spelling this wrong. So let's take a look at our model here. Go back to the model, get rid of these lone pairs, and add 1, 2, 3, 4, 5, right? So let's take a look at this. You can tell there's 2 kind of above and below, and all those bond angles are 90 degrees. And then you have 3 that are in the same plane, and they're all 120 degrees. So there's trigonal bipyramidal. And then, of course, we can play this game where we replace one atom with a lone pair, so something like AX4E. So example would be sulfur tetrafluoride. And so this one's going to have a lone pair. But now we've got 2 different types of atoms, right? We've got kind of this one above and below, and then we've got these 3 in this plane. So think about which one you're going to want to replace and what the bond angles are. If you replace one of these, then you're putting a lone pair at 90 degrees between 3 things. And so that's pretty close. Whereas if you replace one of these guys, you have 2 at 90 and then 1 at 20. That gives the lone pair more room. So you're going to replace one of the ones in this kind of triangle, what we call the X or the equatorial electrons. So this is correct. Whoops, these are all supposed to be F's. And this one on the right is not correct because you have more interactions between these lone pairs and these electrons. There's just more repulsions. The one on the left gives the electron by itself better. And so again, the electron geometry always stays the same, so it's still trigonal bipyramidal. And what we call this molecular geometry, and you'll see why in a reason, is a seesaw. So let's take a look at that. So let's get rid of one of our things or one of our atoms and replace it with a lone pair. And you can see in the bottom left, the molecule geometry goes to seesaw. And so let me just kind of put it in the correct orientation where it looks like a seesaw. So kind of like this, not perfect, but you can tell like one of them is the base and then the other 2 are sticking out. So it looks like a seesaw, right? So I mean, there is kind of logic in this naming. Don't know if they have the real one here. Yep, there's PCl5. No, yeah, that'll be all 90 degrees. That's a 4. There we go. Right. And then you can tell all these other bond angles will be compressed. Right. So this will then be less than 90 degrees. And then this one will be less than 120 degrees. So there's your seesaw shape. And so we can keep playing this game. We can say, what if we replace 2 of the things with lone pairs? So we'd have AX3E2. So an example of this would be bromine trifluoride. And so we generally draw the lone pairs just kind of like this, even though in real life, one of the lone pairs is coming out of the board and one of them is coming into the board. And so the electron geometry stays the same, still trigonal bipyramidal. The molecule geometry, now what we call this is T-shaped because it looks like a T. So you can see there's kind of logic here. I don't know if they have this one. You're a 5. No. Yeah, it doesn't look like they have an example of that one. So let's just look at the model. So replace yet another one of our atoms with a lone pair. And you can see we have this T shape. And you can see our two-dimensional drawing is not a perfect representation of this because one of the lone pairs is coming in and out of the board. This time, they're both kind of pushing the same amount. So both of these angles are 90 degrees. And then keep playing the game AX2, E3. Example of this is xenon difluoride. So we have xenon here, and then again, we just kind of put these lone pairs like this, even though that's not an accurate representation of where the lone pairs really are. And you can see this time it just reverts back to linear. Just stays in a straight line, but it's a different kind of linear. And all of these bond angles are 180 degrees. So let's take a look at that, get rid of one of our atoms and add another lone pair. And you can see it's linear. Of course, the electron geometry is still trigonal bipyramidal. And that's it.